Okay, so we are talking about vector algebra, and there are two operations. Therefore, there will be properties similar to the properties of the algebra of numbers associated with both of these to begin with, and then there will be mixtures. Okay, so we have vector addition. And that's what we have been talking about just now. The last one was associativity. Okay, you can see how it is the order doesn't matter. Whether you have parentheses or not works out just fine either way. So that's what I tried to do last time. Well, maybe not this, but I was trying to do something. That is the same quadrilateral, right? So why is it the same left-hand side, right-hand side? Because we're talking about the same point, right? So it's quadrilateral, 1, 2, 3, 4 points, same as these. So naturally, it doesn't really matter which way you proceed from the beginning, say from P to Q. There's or rather, it doesn't matter in which way you connect those intermediate locations. So on the left-hand side, I first connect from P to, I don't know, S, and then to Q. Or I first connect from, say, R to Q, and then I connect this point to the original point P. Okay, the order then won't matter because it's the same quadrilateral. The misleading, there is a misleading part here. The misleading part is that this is, it is not really a quadrilateral because it's only quadrilateral if it is on the plane. So technically, 4 points might be lying in three-dimensional space. So you think of this as a three-dimensional situation. So 3 vectors, 4 locations, which might not fit on the plane. Okay, so imagine that. A and B are, well, two vectors always do, so A and B might lie in the same plane, but the third one might not. So you can imagine this is AB and this is C. It is quite possible. Then this picture, even though the locations are still the same, but then it remains to be demonstrated that indeed the beginning location and the end location is the same. When it is quadrilateral, it is exactly made of the same points, I suppose. But generally, it does require proof. So we're not doing proofs in this class anyway. So let's just convince ourselves that this seems plausible. And so we have associativity of vectors based on our understanding of three-dimensional geometry. And later on, shortly, we're going to demonstrate this based on the coordinates, or the components of vectors. So let me do one more, and there's one more property of vector addition. So entirely apart from the scalar multiplication, there is one more thing, and that is the zero vector. The zero vector. There is a special vector 0, which is, when added to any other vector, gives you the same vector. So A plus 0 is equal to A. Well, so imagine that the vector, the 0 is, you can think of it as O, letter O rather than 0, even though we do refer to as 0 because it serves as the analog of the 0 number, but this is not a number anymore. All of these are vectors, so that is also a vector. I intentionally don't use any arrows, but remember this is also a vector. So do not confuse numbers with vectors. That's one of the challenges of linear algebra, that we mix vectors and numbers, and they're not to be confused. So this time 0 is, that's more confusing that we use the same letter for the number and for the vector. Well, so the context should tell you what it is. In particular, that if you know what the other item A is a vector, then it is going to be, then you don't add the number to a vector. Okay, so if these two are added together, then if one vector is, then the other is 2. Also, I will stick to, once again, that convention that I'm going to be using capital letters for vectors. and lowercase for numbers. Okay, so then it's the same vector. Okay, the logic still applies. You know, you translate the vector, put it at the endpoint of the new vector. Well, what is that new vector? It's like this. Oh, if you like. Okay, so that's might look a little bit weird, but you know what I'm talking about here. What is that? The meaning of that on the right? Well, good question. What is it? Is there operation between them? No, these what? These are not numbers now. It's a vector from 0 to 0, from the origin to the origin. Okay, so if we have our Cartesian system, we have the origin here somewhere. Well, if a vector, we always define vectors by something that connects to points, and if it's the same point, well, 0 from 0, that's how we technically would write it. O is our 0 vector from the origin to the origin.
So is that different from the coordinate, which would be just 0 as the origin? Is that different?
Well, it is different primarily because 0, 0 in parentheses would be a two-dimensional situation necessarily, while this notation applies to any dimension. So it's literally from, I mean, if there any doubt, put just an arrow above it to indicate that it is indeed a vector, and it is determined by the initial point and the final point. Okay, but it certainly looks awkward, and that's why we're using just O or 0 for that vector. So that's how most of the books do it, either with the arrows or they make a boldface 0. It is 0 still, not 0, not an O. O stands for the origin, the point on the Cartesian plane or space. Okay, so that's why on the right I have two O's, and on the left I still have a 0, which might have an arrow above it, or it might have a boldface presentation, but I'll try to avoid that. So I will be referring to as 0, and I will be writing 0 rather than so it's a letter. Okay, so that's fairly transparent, and there is the another property. The name for it is, I don't think there's a good name for it. The 0, no, the, where is it? Well, there is no good name for it, but let's say the inverse. There is minus A, such that A plus minus A is equal to 0 for each. So each vector has its inverse, the one that cancels its effect. We certainly know what it stands for. It's the vector that points in the opposite direction of the same magnitude. But the point is that it's always handy there available for us. I don't want to put it in terms of coordinates just yet because I want to have these properties standing on their own, and then we'll be able to refer to those properties directly rather than rely on coordinates, which is always cumbersome and also dependent on our choice of coordinate system. The coordinate systems vary even though they produce the same algebra. Okay, so like I said, it's that is quite predictable. If this is A, then A minus A rather points in the opposite direction like this. Okay, so that's the cancellation. If you think about, if you plot these two, and once again you try to how do you add two vectors? You take one, so I take A over here, and then I take the other one and align its beginning with the ending of A, so like this. Right, so I align them together, and indeed the addition will produce like this, will bring me back to the origin. Okay, or vice versa. The order doesn't matter, as we know from the commutativity property. Okay, so there are more properties, but I don't want to overwhelm with the number of properties. We already have 4: commutativity, associativity, and zero vector and inverse. Okay, so referring exactly and exclusively to a vector addition and nothing about scalar multiplication. So let's just revisit this now in the light of component representation of vectors. Still in low dimension. So components are of a vector. It is really uncomplicated. So if, say, A is equal to, if P is equal to 1, 3, then OP, the vector, is 1, 3. Okay, so that's pretty much the whole idea of components right there. We have defined vectors in terms of points, right? The location they connect. Okay, so OP connects the origin to the to point P. So this is 1, 3, 1, 3. Okay, and it doesn't really matter. If we understand points, then we can use that understanding to understand vectors. So if OP, we understand all the points, we understand the relation between points and pairs of their coordinates, right? So this is 1 and this is 3. That's the meaning of the coordinates of point P1, 3. Then what we do? Well, what about vector? And this is my vector, OP. And now, then certainly if two numbers determine the endpoint of the vector, with the initial point is the same as being the origin, then we only need two numbers to determine the vector. Okay, so that's the whole idea. Certainly, you can think that high dimensions. So you can 1, 2, 3, 7 in 4 dimensions, right? Then OP is, once again, I'm using different notation just to keep things apart, but these numbers are the same. Okay, so the difference is primarily is that so once again we keep these call these coordinates, which is natural. You know, it's like talking about maps. This is my coordinate. It really, you don't want to speak of your location as a vector. There is no vector there. It is a location, and you know this is south, this is north, this is how far north you go, how far west you go, and that these two numbers give you the coordinates. A three-dimensional one more number. And then to these we refer as same numbers, but we refer to them as components. Want to guess why they're called components? Well, think about the word component. So it's we're talking about they compose, these two numbers 1 and 3 compose our vector. How do we compose vectors? Well, there's only one way. We add them. Okay, so can you somehow add 1 and 3 to produce 1, 3, like on that picture? This is one, and this is the other. Okay, so what? No, it's not. No, it's not about Pythagorean theorem. No, it is a component. We choose the two directions that are chosen ahead of time, x and y axis separately. Okay, so we decompose our. Suppose we're talking about motion, maybe. So there is a horizontal motion, there is vertical motion, and they're happening independently. So then we're looking at how far we went. Horizontally, it's 1. How far we went vertically, it's 3. Okay, so that's the decomposition, and that's why we refer to them as components. Because why? Because if I add those two vectors, say this is A and B, right? So then A plus B is our vector OP. So we decompose our vector, every vector, into the sum of two vectors that have a particular directions, usually along the axes that were chosen ahead of time. So it's only changes when you have four main directions along the axes, and once again it will be decomposed into four components relative to your, say, displacement, relative to each of the four dimensions, or four directions, four basic coordinate directions. So, there is a more specific way of doing it. Slightly, it is there are names of these particular vectors like this. So, the Cartesian system, which we have been introduced as a way to handle points only. Now, to handle vectors, we don't really do a lot more. We just introduce two or more special vectors. So, in dimension 2, there is a vector. This vector is I, and this vector is J. Both of them are unit vectors. In other words, they have length 1. So they go, well, I could simply write what they are. I is equal to 0, 1, and J is, what's J? 1, 0. Okay, so it's like the building blocks. I and J are the building blocks of all the vectors. I can represent every vector in terms of these. So meaning what? So I'm going to, once again, to my vector OP, which is 1, 3, and how do I represent it? It will be I plus 3J. So that's the decomposition. That's why not I and J are, but we are referring to, well, this is 1, as these as the components. So how many I's there and how many J's there? How much of the horizontal, how much of the vertical we're dealing with? What? 1 I plus 3 J's, yes. And then in 3 dimensions you'll have one more, usually called K. So like this. So this is K. And so once again, if I have a vector, say 2, 3, negative 2, then it will be 2I plus 3J plus negative 2K. So once again, this is I, and the green one is J. Along the axes that were chosen. In higher dimensions, this doesn't work as well anymore with the same. You run out of the letters in the alphabet, so you have to number them, and rather than having X, Y, Z, you have X1, X2, X3, X4, X5, and so on. With the same with the basis vectors. But at this time, practically speaking, that representation over here is sufficient to understand what a vector is. Those numbers give you, if you want to go backwards, what do those numbers mean? How do you visualize that vector? You find the point in the space 1, 2, 3, 7, and connect and draw a vector from the origin to that point. This point. Okay, so points, it is the endpoint. In other words, that's the explanation of the relation between the coordinates and components, the relation between the location of the endpoint. The coordinates, the components are the coordinates of the endpoint of the vector. Okay? Did I say it right? Once again, the components of the vector are the coordinates of its endpoint. Okay? Yeah, maybe, too many words maybe. I myself keep saying coordinates when I'm supposed to say components, and vice versa. So it's not such a big deal. Okay, so I want to now, what it is actually, this is will make our much easier in a sense when we talk about algebra. So because all of these properties now turn into properties of real numbers. So the algebra of real numbers now reappears not only in the algebra of vectors, but it will also manifest itself as the algebra of components. Right? So if we start with commutativity, for example, then this was written and meant to be a commutativity of vectors, right? Addition of vectors. But what is happening to every component of these vectors? They are being added, right? Okay. So and the same with well, we're starting with addition. So all these properties will reappear, and so will the ones about scalar multiplication. But let me make that clear. So so the question becomes how do we add vectors represented by their coordinates, components, obviously. Well, the answer is very simple. You just add component by component. Just keep them aligned. X's with X's, Y's with Y's. Okay, so it's really simple. 1, 2, 3, 5 plus 2, negative 1, 0, 3. Add together, align them, each component by each component. Remember that you might be dealing with things that are not related. So one component might be x-axis is time and y is space and z is temperature. Okay, so don't mix them up. And this one will be 1, and this will be 3, and this will be 8. It is certainly worth observing how it happens. So I have a spreadsheet that's supposed to illustrate this. So I hope it works. You didn't say?
Can you add vectors that don't have, let's just say you knock off the last component,
Yeah.
the bottom one there, would you still be able to add them and just have that as 0?
No, we do not add vectors of different dimensions. They live in different spaces, so they must have the same number of components. Right. The only exception is 0. Is 0? You can it's usually treated as if it might belong to any space of any dimension. So 0, 0, then yeah, you can as many zeros as you need. But generally the rule is yes. So within the same Rn. So this belongs to R4, and this one belongs to R4, and the end result also belongs to R4. Same with distances. Can you measure? Well, obviously, if you have 2 points, they have to lie in the same space in order to be able to connect them together. So so this is the addition of vectors. Okay, that's what I was going to show you. Okay, so so as you can see, what's happening here is component wise addition in dimension 2. Okay, so I start with 2 vectors, green and red, and there you can see them at the top. Can you see A, B, and C over there? Right above the pictures. Right. So I'm not sure why. I guess they're kind of fractional, but only the reason is so I could actually show you how I can vary these without actually typing anything, so that it would be kind of interesting to see what's happening. So I think this is, let's see. Oh yeah, I can rotate it. Okay, so that's why it's interesting. And you can see how addition changes. So the picture, the original 2 vectors illustrated top left, then they're aligned the way we have spoken of, assigning a copy of the green one to the end of the red one, which is B. I think, which one is B? A is B. Yeah, A is red. Okay, then I connected by the diagonal, or not the diagonal, but rather the beginning to the end with the blue one. That's my C on the left, and then the alternative way to do it is with the parallelogram. So that's the other 2 pictures. Okay, and you can see if I start rotating A, you can see how coordinates change of A. You see A numbers are changing. B remains intact. All I'm doing is rotating A, and as you can see, everything is changing in unison. Okay, so the coordinates are obviously two arbitrary numbers. And that's supposed to work just fine. Well, I guess it's stuck. Okay, let me try to rotate this one. It is doing a little bit of resizing, but I hope you can see that what's happening is what's supposed to happen. I guess the second picture is the most revealing. You can actually track what's happening with the coordinates. Look, the first two pictures. So you can see the coordinate, the x-coordinate of the red one, A, is 1, okay, and the one of B is like what is 1.8 or something like that, 1.72, okay. Add them together, right, in that row over here. These are x's, right. They added together component-wise from left to right. And the end result is 2.27, which is here somewhere. Okay, that's the sum. That is the blue one is the sum vector C, and you can see clearly where that vector is. So it's happening entirely independent, one coordinate from the other. And then, so if I do now look at these are the y coordinates or components. Then the 2 is the value of A, and B is 1.43. So together it's 3.43, and you can see how that is happening here, at least numerically. But you can certainly see two right triangles here. That's another way to see it. So one right triangle, 1 by 2, and the other right triangle is 1.72 by 1.43, and then naturally one gives you the vertical difference, the other gives you horizontal, so you don't mix up x's with y's. So there is really nothing mysterious happening about it. So I want to, well, there's also, I didn't talk about it, but since we're talking about algebra, we should be able not only to add vectors, but also to subtract. Okay, so well, once again, without invoking any scalar multiplication. What is a subtraction? It is the inverse of addition. So there's another one here. So this is the subtraction. Okay, so you can see that that's the second picture is what you should keep in mind, have in your mind. It is so you don't have to, for subtraction, you don't have to move the two vectors, but rather you have to first find that blue vector that connects the ending of the second one. Look at it. The B is the second one. Take the endpoint of the second one and connect it to the endpoint of the first one. See it? The blue one from green to red, and then you need to move it. So that's the third picture. Indicates the last step indicates where that vector is. It's supposed to be located. Okay, so they all supposed to ultimately end up with the initial point at the origin. So that's what we're seeing here. Okay. Okay. So now, okay. So and now let me illustrate the. What is this illustration of? Yeah, and adding in them, yes, but you see how you proceed from left to right, and then you split. It is commutativity, right? So either A plus B or B plus A below, okay? And then the third picture is supposed to demonstrate that it's the same. The result is the same. The blue one on top, the same as blue one at the bottom, right? Okay, so that's supposed to illustrate commutativity. And once again, I could, move stuff around just for fun. So it's not a fix. It's actually a spreadsheet. It computes this stuff for various. I can vary these things if I want to. Okay. So actually, I should have started with the. Well, that's fine, I guess. So now. This is associativity. Okay, let's take a closer look at it. So once again, it's carried out, the computation is carried out in the same way as before, coordinate-wise. So it's you certainly cannot do this without spreadsheet. You need numbers. So you plot, you take those numbers. The numbers once again are here. The three vectors are listed A, B, C, and D. So here A, B plus gives me D, and then I add C, and that gives me F. Okay, or I first do B plus D, and then I add A. Okay, so it's numbers are obviously just used for illustration purposes, so to produce these pictures. So once again, we'll proceed from left to right, and we have two versions. So like it's an equation, it's a property, two things are equal to each other. So I want to demonstrate that the upper route is the same as the lower route. Okay, so three vectors are given, A, B, C. Okay, then what I do is look on left, the top. Let's go along the top path. So red plus green, A plus B, gives me D, the light blue one. Or the light blue one is D, A plus B. Okay, so far so good. Then I'm picking vector C, the purple one. So D is equal to A plus B, and at C, I'm getting F equal to D plus C. Okay, so it connects right to the endpoint. Okay, so the yellow one is supposed to be our sum. The yellow one. Okay, now I take the other route. As you can see, the order changes. I have a copy of, I don't know, I'm adding B plus C first. B plus C, and then I'm adding, gives me the blue, okay, which is E, B plus C, and then I finally add red one, which is A. And once again, I have a yellow one, and then the question becomes, is it the same thing? And as you can see, I guess you can, I'm not sure if it is, the last three pictures supposed to demonstrate it is the same thing. Well, certainly, it is really easy to prove, actually. It is easy to prove. This is sometimes visual proof is less convincing than numerical one, and that's the example of it. So even though yellow, that goes on top yellow, go on bottom yellow, they clearly look the same. In fact, you can see that both of them are 4, 5, right? The yellow vector is 4, 5. So at the end, makes sense, right? But with numbers, actually, it's much easier, and so we're gonna do that next to see that, just to illustrate how it works. And it works based on the commutativity and then associativity properties of numbers, right? So say let's do commutativity. So let's dimension 2. Say we have a vector A, B. Let's make x1, x2, a1, a2. B is equal to b1, b2. Okay, if I add a plus b, we know it's supposed to produce a1 plus b1, a2 plus b2. That's what component-wise addition is. And okay, so let's flip it. B is equal to b1, b2. A is equal to a1, a2. B plus A is equal to, so already feels kind of silly, b1 plus a1, b2 plus a2. Okay, so we look at this and what do we say? They're the same. Okay, can you justify it? Because, well, you can. Well, one issue is to be addressed. I think it's sometimes overlooked with the complexity. It's easy to overlook what it means for two vectors to be equal to each other. Their components are equal. Okay. So the same, what in the first, before we prove anything, what does it mean for the two vectors to be the same? So I'm saying that a plus b is equal to b plus a, as we stated previously and illustrated with those pictures. What does it mean in the first place? And it means that they are equal component-wise. What does it mean to be equal to component-wise? That the first components are equal, the second components are equal, the third components are equal, right? So if those components are equal, then the endpoint is the same, and it's the same vector. Okay, so it's once again, it's fairly predictable. Okay, the only issue here I have is why. So we answer this question. We do want to claim that these are equal in the sense of being equal component-wise. So what I'm saying here is that A1 plus B1 is equal to B1 plus A1, and A2 plus B2 is equal to B2 plus A2. Okay, so that's why they're equal. If we can claim that these are equal to each other, those two, for dimension 2, if these two pairs are equal to each other, then the two vectors are equal to each other. But how do we know that these two are equal to each other? These are equal to each other. How would you justify it in one word? By commutativity of numbers, right? So components are numbers, and if we know anything about numbers, we certainly bring it to the table and we use it. So then commutativity, we can flip the addition of numbers, then we can flip the addition of vectors. That's what we discover based on this. And the good news is, obviously, this is dimension 2. Is there any challenge of if I go to dimension 3 or 53? It doesn't matter. Component-wise, it will just, those strings will have 50 components, but I still do it one at a time. I flip them, and and I come back. They come back the same, and the justification is every time is the same. Commutativity property of numbers. Okay, so commutativity property, commutativity of vectors. So commutativity of vectors, that what we care about right now. Where does it come from? It comes from commutativity of numbers.
Okay, they are equal what?
To each other.
I know we have the top line.
Component.
Okay.
Component, yeah, so component-wise, yes. You can almost see every. Okay, so that's the rule that applies pretty well. So that's the idea. Algebraic properties of vectors follow from the corresponding property of numbers. So then you can guess commutativity of vectors comes from the commutativity of numbers. We demonstrated this. Now the next issue would be what about the associativity of vectors, of addition of vectors, that is. And the answer is it comes from associativity of addition of numbers. I missed the word here, addition. Commutativity of addition of vectors follows from the commutativity of addition of numbers. So not to be confused with commutativity of multiplication of numbers, for a simple reason that we do not at this point multiply vectors. So whatever operation is available, we will find a similar or corresponding operation for numbers, and that will tell us how our vectors behave with with respect to that operation. So commutativity, addition, let's follow on with the, so then let me just write it out, the associativity of addition of vectors follow from the associativity of addition of numbers. Okay, so that's number 2. And we have 4 so far. So hold on, where am I? Empty page. What happened? For associativity. Okay, so that's number 1, commutativity. There are 2 more properties. I have 2 empty pages for some reason, and I don't know how to do with them. Nope. I'll figure it out. Okay, so number 3. Number 3 is the 0. So what do we do? We just say the 0 vector, and we specify what it is. So 0 vector is given in terms of its components. So it's easy to guess what it is. It's just a bunch of zeros. So all components are 0. Okay, so special vector, think about it. It's supposed to, when you add the 0 vector to any vector, there is no change. Okay, so how do we accomplish that? We add 0 every time. Okay, so the good news that we have for a special vector, we have a special number that makes up that vector. So having a 0 as a number produces a 0 a vector. And fourthly, the inverse. So if I have, if my vector A is A1, A2, AN, negative A, once again, it's the inverse of every component. So it will be negative A1, negative A2, negative AN. Commas here. Okay, so that works out pretty well. So component-wide addition, that's produces these 4 properties. They become more specific. They last to give a specific formula, very specific formula for that 0 vector. So it's not something just that we have to make up. We know what it is. And the inverse also, we don't have to make it up. We know what that vector is. That cancels out our vector A. So if you try to add these 2, of course, you end up with 0. Okay. So now, unfortunately, that's not it. Even though we have 4 properties already, and we took 2 angles, ways to look at them. There's the second operation. There's the second operation, and that's scalar multiplication. So we have to go through the same analysis. This time, scalar multiplication. It is simpler, obviously, but once again, let's be careful. Scalar multiplication. And what algebraic properties it has. Initially, we start with free of coordinates to begin with. The properties are fairly simple, and that is, well, there are only 2. Oh well. So where do they come from? They come from, if you remember, properties of a multiplication of numbers. There is only one really we care about. Property of multiplication of numbers that does not involve addition. What is that property? It's associativity again. Okay, so what we're talking about then, that's what I'm talking about. Say, A, B, A is equal to A, B, A. That's associativity. So associativity of scalar multiplication. Okay, so in other words, just like with associativity of addition, you don't care about how you carry out that operation. Like grouping terms, doesn't matter how you group the terms, the result will be the same. So as you can see, these are two technically different operations. I first multiply A by B, and then by A capital by B, and then by A. Or I first take care of the numbers, that's on the right, and then I multiply. It's really not very hard to illustrate because, well, with just examples, say B is equal to 2 and A is equal to 3. So over here I start with vector A, and then what do? I double it first. So this is A, this is 2A. And then I triple the result. So the triple like this. So this was my 2A, 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 right? So altogether, that is my left-hand side. That's my left-hand side. So I multiply it by 2, and then the result is multiplied by 3. Okay? So A, 2A, and then 2A repeated. Or what do I do on the right? I take my 2, I take my 2 and 3, and first multiply them and getting 6. And only then I finally multiply vector by 6. So I have vector, and I just have it 6 times. So this is 6A. A, 6A. So this is the left-hand side, and this is the right-hand side. Okay? Needless to say, it's the same. The outcome is the same. Okay? So explaining it with the we can explain it with the coordinates, components as well. So just we need to understand how do we multiply. What is the meaning of scalar multiplication? So not too complicated. Say I multiply vector 1, 2 by 3. How? Once again, component-wise. So it will be 3 times 1, 3 times 2. Okay, so 3, 6. So that's the way we carry out scalar multiplication. Once again, component-wise, without geometrically. Remember, scalar multiplication is a stretch. If it is a number like 3, you stretch it by vector 3, but it doesn't really matter if you care about components. It is a purely algebraic operation that's I carried out right here. When it's number negative, then it's also there's a flip. If there is a number, say 1/2, it is a shrink of the vector, but algebra is the same, so you don't really care. You can multiply by 3 just as successful and easily as you multiply by 1/2 or negative 1/2. You can multiply by 0. Okay, so that's an interesting question. What happens when you multiply a vector by 0? 0 times A is 0. Okay, except what is tricky about this formula? That's right. So this 0 is a scalar, a number, but these two are vectors. And so, well, obviously A meant to be a vector, but this 0 on the right is not a number anymore. It's a vector. So it's scalar multiplication that produces a new vector. So, okay. So we'll just continue this next time.